Hey kiddos. So we're about to start the last unit before winter break. And in this unit, you're going to learn all of your integration techniques. So you already know two. What you know so far, uh, uh, or what we've tried to work on so far, are all of the things that integrals are and what they do and what they mean. And now we're going to focus on how to take them. So the first thing that you already know how to do is you know how to undo a derivative. So like the back of a flashcard. So anti-differentiation. The other thing that you know how to do is to take integrals when they're geometric and you can like turn them into triangles or semicircles or things like that. So today's technique is called U substitution. So the problem with integrals, the reason that kiddos tend to find these a little bit more difficult than derivatives is there's not like rules. There's not like every time you see this, you do this kind of thing. But there are these techniques and you need to know which technique to use in each problem. So we're going to do 3 and maybe by the end you'll have an idea. Here's our first one. So first off, go through your options. This is not the back of any flashcard I have ever made, so this is not an antiderivative I can just take. I can't graph it and find the area under it, so it must be U sub because that's all I know. The first time through this, I'm just going to do it, and then we'll talk about why I'm doing it. So there was a time in your life, I think it happened in like Algebra 2. Do you remember when you had to factor things that looked like this? And someone said, well, let's make it easier by subbing in a new variable. And so then you were factoring this, and that's much more manageable. Well, that's exactly what we're going to do here. So we're going to come and we're going to set a new variable, and it's called U substitution because people generally use U. For ours, for this question, we're going to make it x squared. Don't worry about how come right now. Just go through the process with me. Okay, so the other thing we need, we're going to go sub everywhere there's an x squared, we're going to replace it with u and find all of our other things with that. But the other thing we need is we need what du equals. And du doesn't make sense by itself. So think of it as du over dx. It's the derivative of u with respect to x. So that I can do. That's 2x. And then if I multiply it over, du equals 2x dx. Okay, I know you still don't know what's going on. That's okay. So I'm going to come down here and I'm going to rewrite my entire integral without any x's, only u's inside. So the first very obvious thing I see is that I can write this now as the sine of u. And then I hope by now you understand that these are areas of rectangles. So this is the height of my rectangle. The width of my rectangle has to be du. It has to be a u because that's the variable I'm using now. So then I go back and see what is du. Well, du is equal to 2x times dx. So if I look into my original integral, has an x and it has dx, and that's taken care of here and here. Oh, but look, I have an excess 2. I have a 2 that I don't want. So instead of just rewriting the whole thing, I think I'll just pull out a half, and that's going to cancel with the 2 that's hidden inside of du. I'm pausing for a second for you to process because that's the tricky part with U substitution. Once you have it rewritten, it should be a really fast integral. That's the point. Like now this is something that I can do with just an antiderivative or undoing a power rule or something. So what do you take the derivative of that gives you sine? Negative cosine. And that is almost the end. The last thing you have to do is you have to go back and put it in terms of x. So this is negative 1/2 cosine of x squared plus c. That's it. That's U substitution. So since this is our first go round, let's go check our answer. And I check an integral by taking a derivative. So we're going to differentiate -1/2 cosine of x squared. All right, there's a chain rule here. That's what u sub does, is it helps you with your chain rules. So I've got a -1/2. The derivative of cosine is negative sine, so it makes it positive, times the derivative of the inside is times 2x. Oh, look, the 2 canceled with the half, and that half is the same half that I had to pull there. So good job, us. All right, that's u sub. So let's talk about how I made this decision to let u equal x squared. When you're choosing what u should be, you want to find something in your integral whose derivative is also in your integral. So u can't be something very complicated, because that would make a more complicated, like if u was sine, then du would be cosine. There's no cosine in my integral. So u is usually something pretty quick, and it just cleans up your integral sum. So here's another one. X cubed times 2 plus x to the 4th to the 5th dx. Theoretically, you could do this question without u substitution. You could multiply this out 5 times and then distribute in an x cube. But I have other things to do today. So we want to find something in here whose derivative is also in here. I hope you're seeing this x to the 4th and this x to the 3rd. So typically students say to me that u should be x to the 4th. And that's a great start. But I want to encourage you to include constants in u, because when you go to take du, they go away, and then they're not a problem at all anymore. So du is going to be 4x cubed. Remember, it's du dx, so when I multiply over the dx, there's a dx here. Okay, let's go rewrite our integral using only u's and no x's. So obviously the first thing I've got here is u to the 5th power. I have to have a du or my integral doesn't make sense. And let's go see. Du has x cubed and dx, so x cubed and dx, but it's got this 4 that I don't want, so I'm going to multiply by a 4th on the front. Again, I'm always going to pull my constants out front, completely out front, so that they don't get in my way of integrating. Now it's quick. So I have 1/4. I'm going to add 1, divide by the new, so I have 1/24. Remember to go back and put your x's back in. So this is x to the 4th plus 2 to the 6th plus c. And again, it's a pretty quick derivative to take to check. You're going to pull the 6, reduces down to a 4th, and then you have x to the 4th plus 2 to the 5th times your chain rule is a 4x cubed. The 4 cancels with the 4th. There's your x cubed. The end. Last one. Okay. You want something in here. Oops, sorry. You need to choose a u whose derivative is also in the integral. You want something in there whose derivative is also in there. So the problem with this integral is that it appears as if you have a lot of options. And honestly, sometimes you do. But let me go through the most common options that you kiddos tend to choose. Some people will go straight to secant. That would mean that du is secant x tangent x dx. And that's pretty okay, because then if I do a u du, I have my secant squared. Oh, but I only have a single tangent. So that's not going to work for us. Let's pick something else. Sometimes then you children say, if I need a tangent squared, I'm going to make a tangent squared. But this is the situation where you're making u too complicated, because then your du involves a whole chain rule. And the whole point is that you shouldn't have a chain rule. Do secant squared x dx. So again, I'd have a secant squared dx, and that's great. But this time, if I put these together, now I have a tangent cubed, and that's a problem. So the correct choice to make here is just a single tangent. All right, because the derivative of tangent is secant squared. Now, when I go to rewrite my integral, I need tangent squared, so this is going to be u squared. And my du is going to take care of secant squared. All of this is inside of du. And then this is super fast. U cubed over 3. Put your x's back in. So this is a tan cubed over 3. Really fast to check. Pull the power, subtract 1, chain rule the inside, the end. All right, we will practice more the next time I see you. Let me know if you need anything.